Okay, so today's question is a probability question. So inside here we have the question here, let X be a continuous random variable whose distribution has density, this thing. Over here we have two cases. When it's smaller than C, we have nothing. When it's bigger than C, we have kx, negative theta, negative minus 1. Where C and theta are positive real constants, okay? Given theta and C, find the value of k. Okay, this is pretty straightforward. I think I just wrote down the function here, and then what I did was that if it's a density function, then I know that the area under the curve would be 1. So I can just write the integral of f of x dx is equal to 1. Since I know that the previous part smaller than or equal to c is 0, then I can just take the sum of the right-hand side, should be that thing. So then I go from c to the infinity of f of x dx equals to 1. I take the integral of this is equal to 1. I plug in the values. I know that infinity to a negative power would definitely be underneath it would be in the denominator, so then that would tend to 0 tend to 0. So then I know that I'm left with this thing over here. And I just rearrange it so that my k is on one side, and I move my c and theta over to the other side, and I get that k is equal to theta times c to the theta. And then next what I do is in part 2, I'm asked to find the CDF of x. Okay, CDF is just basically everything from the negative infinity up to that point, right? Since everything in the smaller than equal to c is 0, because before everything there is 0, so there's 0 plus whatever is 0. So then we just have to deal with the part that f is greater than c, x is greater than c. So then we write the integral from starting with c because everything before that's 0, so we don't need to care about it. So if everything from c up to a point t, f of t is equal to this. And then we have our function, and that our thing over here, it would be theta, c to the theta, x minus theta minus 1 dx. So then we just take the integral of this from c to t, plug this in, and we get this. So then this would be our function over here. I could have written it more nicely in the form of c over x to the theta. Um, and then there's a negative sign. It would have looked like this. This would have looked nicer than this over here, plus 1. This would have looked slightly nicer. And I can even move the 1 to here so that it would look nicer. That would have been this. This is equivalent, but I just wrote it in that form because I didn't simplify. Next, part 3, let's go to here. For which positive integers k does m of this thing exist? So this is the moment generating function rather than the PGF. So calculate the expectation of every k for which it exists. Okay, so I was first jumping into like PGF because I thought, okay, yeah, great, this is this thing. But I just realized that this was k to the x, this is x to the k. So this is a different thing. This is moment generating rather than probability generating. So then we have to use inside here. If it's moment, we use the definition of expectation. We're just going to ignore the part with 0 because it doesn't matter. It's not going to change anything. So the expected value of x to the k would just be the thing from c to infinity of x to the k times f of x, the density of that dx, right? That's standardized expectation definition. And from that, we just plug in f of x from earlier and we get this. Oh, I forgot to write dx over here. I should add dx. So then here I get this expression. I can then plug in c and infinity over here. And great, I get this expression. That was what I did. And I kind of argued for it to be defined because I know that this thing has to be defined. So then I know that k has to be smaller than theta. Another way, faster way is up to this point, I know that it has to converge. So the exponent on x should converge so that it has to be less than minus 1. So then k would have to be theta. So I would arrive at the same conclusion. And then next what I do is after this, since this thing tends to 0, then I just have this term left over, right? So now I know that my thing would be k divided by k minus theta. Um, minus this. Yeah, so then it would be this thing. I just do a bit of algebra, manipulate the variables, simplify it, and I get this. And that would be my answer for MK. Obviously, my answer in the final thing was slightly different. I think this is written in a different form because I kind of already I thought that my first idea was to write K, every K in terms of theta and C to the theta. So then that was why I got a different answer than this. But it's essentially the same thing, just written in a different form. I'd say the steps, I'm not sure if this is correct or not, but the idea is that from this point, once I got to this point, it's just basic algebra simplification. Inside here, what I did was that I kept the k on the top. Like I only replaced this k, but I did not replace the denominator k. The k on the denominator remained the same. I only replaced the top k over here. Like I replaced this k to be C theta C, which I did earlier. And then that way I could cancel out this term over here. And then I just moved the negative sign into the like swap the order of the thing over here. So then I get it to this form, which slightly looks nicer than this. But I think it doesn't matter which way I do it, ultimately. So that's it for this question.